Okay, so we're going to pick up where we stopped last time. We were going to finish up proving the Eckert-Young-Mirsky theorem. So what we were talking about was the low-rank approximation of a matrix, right? And if you remember, we looked at this demo with the kitten, right? Where you were looking at how can I minimize the storage that is required to store all of the pixels. And we were saying that there's two ways in which we can think about, a matrix norm. One way is to think about the matrix as being a chunk of data, which gives us the Frobenius norm. And the other way is to think of the matrix as an operator, which gives me the spectral norm, right? And these are the two different perspectives. And turns out that if you try to solve this low-rank approximation problem, so approximate a matrix A with another matrix B of rank at most k, the solution to these optimization problems are identical whether you're considering the Frobenius norm or the spectral norm. And last time we started out with the spectral norm proof. We just had a little bit to finish. And how did we start out with that? Well, we noticed basically that if I look at A minus AK and I look at the 2 norm of that, this we noticed was the k plus 1th singular value of the matrix A, right? Remember, the singular values are always arranged in decreasing order, descending order. So you always have the property sigma 1 greater than or equal to sigma 2 greater than or equal to sigma r strictly greater than 0, and then sigma r plus 1, and onwards are all 0, assuming that you have a rank R matrix, right? And then we said that, okay, if I wanted to go about proving my theorem, then what I need to be able to show is that for any other that is at most rank k, if I take the spectral norm of A minus B, this must be greater than or equal to sigma k plus 1, right? So you basically show that you can achieve your bound, and then you show that for any other matrix, you must be greater than or equal to that value, which then declares that AK must be your minimizer, right? We've done this kind of argument many, many times now. This should be familiar to you. Everyone remember what we did last time? Yes? No? Some nods? Good? Everyone with me here? So what was the thing we did when we started? So we want to show this, right? This is what we need to show. This is where we left off last time. What was the thing we did to think about how to move forward? What is the thing that's annoying about this particular expression here? Like, a generic B is hard to deal with, right? We don't know anything about this B, and to say that, we know a lot about matrix A. It's given to us. We know exactly what it is. But B is an arbitrary rank K matrix. That's very hard to deal with. And this, on top of that, this is a matrix norm, right? We would much prefer to be dealing with a vector norm. So can we rewrite this matrix norm in terms of a vector norm? Or can we relate it to a vector norm? Right. What can we in fact say? We can say that A minus B 2 norm is always greater than or equal to the following vector norm. You know where W is any unit vector, right? Just by the very definition of the spectral norm, we know that this is true. Everyone remember this? If you don't remember it, you should be looking at your notes from last week and trying to remember this, okay? So either you're looking at me like you understand what's going on, or you're flipping through your notes, one of the two. Okay, so we're here, and now what do we want to do? The other thing that you've all pointed out to me is that the challenging part of this is dealing with this B. This B is something that we don't know how to deal with because it's arbitrary. So how could we possibly get rid of this B? Right? We now, what, is it clear to everyone what we want to prove now, at this point, from here on? Okay, take a minute, write out what do we need to show from here on. Write this down on your paper. The key to being able to do proofs is you have to write stuff down. Proofs do not happen in your head. They do not happen by thinking or staring at the, like, just, I don't care if you're like drawing pictures, you know, draw flowers and elephants, that's totally fine, but you need to be writing something down. So what do we need to prove now? What is the statement that we need to prove that will allow us to go to where we need to get to? Anyone? How many people feel comfortable about what we need to prove next? Okay. What do we need to prove next? Exactly. We want to compare this quantity, right? We've said that we want to show, this is what we need to show, right? This is what we need to show. But since we know that A minus B matrix norm is always greater than equal to A minus B times W vector norm, it is sufficient to show right? Because that implies what we want to show. So it's sufficient to focus on this case. This is all that remains to be shown. Okay? How do we do that? Yes, question.
Sorry, why?
Okay, think about it. What do we want to show? We want to show this is true. Okay? So now I show that I already know that this is already greater than this thing. If this is greater than sigma k plus 1, can this be any smaller than sigma k plus 1? It's just a chain of inequalities, right? Very simple. I know A is greater than or equal to B, and B is greater than or equal to C. What can I conclude about the relationship between A and C? A is greater than or equal to C. There's nothing different happening there. So, once we have this, how are we going to show this? The thing we concluded last time was that B is the annoying part. We don't want to deal with B. A wonderful way to get rid of B is to choose a W that basically nullifies B, right? So what W do you want? So to remove B, choose W. Okay? What is the problem? What do you have to check when choosing B, W in the null space of B? Can you always choose W in the null space of B? Kind of. Is W equal to 0 a good choice? No, because we need W equal to be unit norm, right? So we can't choose W equal to 0. So what do we have to check? Is the null space of B trivial or not, right? Is the null space of B trivial? No. Why is null space of B non-trivial? Rank of B, or rank of B is less than or equal to K, right? And B is an m by n matrix. K is less than m and n. Therefore, it must have a non-trivial null space. Right? Everyone remember that? Therefore, there must be a unit vector present in that null space. So it's possible to choose this kind of W. Okay, good. Is that good enough for us? What more did we want? We don't want just that. If we did that, so we have now A minus B 2 norm is equal to AW2 norm, right? Just by this choice of W, B times W is equal to 0. Therefore, we've removed that component. So now we have this A times W, and now we want to say, what do we want this to be greater than or equal to? What do we want to get out here? We want to do some algebra, something, something. And what's the thing we want to get out? sigma, which sigma? K plus 1, right? So what kinds of things do you want to do? What other properties do you want to have be true of W such that you can get that sigma K plus 1 out? Look at those eigenvectors or those singular vectors that are corresponding to that, right? So what is the eigenvector that is corresponding to sigma K plus 1? Let's say I have my V, and I write my V as V1, V2, Vk. This is my V matrix, right? I can write this here as U sigma V transpose times W. So I want to look at W in terms of how it interacts with these singular values, or how it interacts with the SVD basis, right? And the SVD basis can mean two things. It can be either related to the U or related to the V. But because here I'm left multiplying by A, like basically it's the V transpose times W, it's going to be to my advantage to think about things in terms of the V basis, right? Because when I have things in the V basis, I'm going to be able to cancel out a lot of things with this V transpose, right? It's going to make my life a lot easier. So I want to think about W okay? In particular, maybe I can think about W is equal to V times alpha. V is a full rank matrix. It's invertible. I can always write W in this way. Nothing prevents me from writing this W in this way. What I want to do is I want to be able to pull out sigma K plus 1. So now, for example, let's say I chose W to be equal to Vn. I don't know that I can choose this, but let's say hypothetically W was Vn. Okay? What would this calculation give you? Why don't you do it out? Put W equal to Vn, and what would you get?
U sigma n.
Just do it out. Write it out. Pencil must touch paper. Something must be written on paper. That is the only way to learn how to do proofs. It's very hard to do proofs by typing. It is very hard to do proofs by thinking. The best way to do proofs that I know of is pencil to paper. Another case for you to think about is like if I think about W is equal to just V times the all ones vector. There's ones everywhere. That might be another good case to think about. No, actually, Vn is easier. This one's an easier case. So what do you get out? Right? What is the alpha? If W equal to Vn, how can I write W? W is equal to now V times, what do I need to write here? If I want to pull out the last column of W, what vector do I need to multiply it by? What is alpha? Last column of V. If I want to pull out the last column of V, which is Vn, I write all zeros and 1, right? In this case, what is U sigma V transpose V alpha equal to? This is U sigma. What happens to the V transpose V? This is identity. And so then I have an alpha here, right? And now what happens when I do this sigma times alpha? What is alpha here? Now we've chosen alpha to be this zeros and then 1, right? Okay? So what happens when I take sigma times this thing? What is sigma? It has all the singular values along the diagonal, right? So which singular value is this going to pull out? The last one. And you're going to pull out a sigma n, right? Is that what you want to be pulling out?
No.
Is sigma n the biggest one or the smallest one? The smallest one. So which one would you rather be pulling out? You want to be pulling out the k plus 1 singular value, right? That's what you want this to be greater than or equal to. So instead of Vn, what might you choose? Vk plus 1. Okay. So if I try to choose something in the Vk plus 1, so question, can we choose W belonging to span of So do there exist unit vectors in the span of Vk plus 1? There do, right? Okay. But now we have this. Okay, everyone see why we want this Vk plus 1 to be coming out? Okay, so Vk plus 1, the span of that is now a one-dimensional thing, right? The null space of B is also some dimensional thing. It's like n minus k dimensional, right? So now, do we have a guarantee that there is a W that exists both in the null space of B and in the span of Vk plus 1? Like now we need this W to satisfy both of these things, right? Do we know that? Do we not know that?
No.
We don't necessarily know that this exists, right?
Yeah.
These are two vector spaces. They might be completely disjoint from each other. We need to have something such that there's an overlap between these two vector spaces. Okay? So how could we amend things to kind of get towards that? Right? So instead of this, if I consider, for example, this matrix, Vk plus 1, let me just define this as V1, V2, Vk plus 1. Okay? What is the dimension of the range of Vk plus 1? K plus 1, right? V1, V2, Vk plus 1 are all orthogonal to each other. They're all linearly independent. Therefore, the space they span must be a k plus 1 dimensional space. Everyone with me there? What is the dimension of the null space of B? Or it must be at least greater than or equal to n minus k, right? Because B is less than or equal to rank k. So it could be n minus k, but it could be even bigger than n minus k. Okay? So now if I add these two, I get n plus 1, right? And what is the ambient dimension that we're living in, right? These vectors are all living in what dimensional space? N-dimensional space, right? These are all length n vectors. Okay?
So if you assume the orthonormal complements, then you have like an n plus 1 space with constants.
I'm not assuming anything. I'm saying that because this is the SVD matrix, V1, V2, Vk plus 1 are orthogonal to each other. And therefore, this dimension is k plus 1.
Right, but in order to add them, like, you have to assume the orthonormal.
I'm not adding anything. I'm just doing I'm just getting k plus 1 plus n minus k. I'm not doing any assumptions. I'm literally doing like 3 plus 2 is 5 level something. Like it's not, I don't want to like confuse it with anything else. It's just this. I'm saying that if I have, okay, this is a bad picture, don't imitate, but like if I have these two things, right? I have to fit, it's like, I have I have something here and I have something here, and I have a total of n spots, and I have one thing that is of length n minus k, and I have another thing that is of length k plus 1, right? And they both have to fit into this thing of n. So there must be at least one dimension of overlap between these two things, right? There must be some intersection that is non-trivial between these two vector spaces, because they're both subspace of an ambient n-dimensional space. But one of them is k plus 1 dimensional, and the other is n minus k dimensional. And because those add to bigger than n, that means there must be at least one entire dimension that they have in common. Does that make sense to everyone?
Yeah.
Okay? So because of this, I can say that there exists some w that belongs to range of vk plus 1 and null space of B. Okay? Because I can say this, now I can write my W. When I write my W in my V basis, what does it mean for W to belong to the range of Vk plus 1? What must my alpha look like? Can there be a component on V1? Right? I can have V1 has something, V2 has something, all the way up to Vk plus 1. But what must the coefficient for Vk plus 2 be? Must be 0. Everything here, all the way, must be 0. All from k plus 2 to n. You with me? Are you following this? So it would have been nice if we could have just chosen W to be in the span of Vk plus 1, for example. But then the dimension of the range of just little Vk plus 1 would have been 1. And then 1 plus n minus k is not bigger than n. Right? Do you see why we have to consider this entire range and not just the range of one of the singular vectors of A? Like, this is the key point, right? What I'm trying to show you is how one constructs a proof. When this proof is normally presented, none of this is discussed. It's always just like, now choose magically W equal to this. Okay? Look, it all works out. What I'm trying to get you to see is how you could do this yourself. This is not magic. This is not painful. This is not hard. It's just sitting down and banging your head a little bit. It's very much within the realm of possibilities, what I'm trying to bring it out. It's not that someone did some magic and therefore we have these proofs, okay? It's just a question of, this isn't working, this isn't working, this isn't working, let's try this, why isn't this working? And that kind of investigative, systematic thinking, okay? And this is the kind of investigative, systematic thinking that is useful to you, whether you're designing a new algorithm or debugging your code or trying to understand your data. What I'm trying to communicate to you is not the mechanics of this proof, or not just the mechanics of this proof, but this thought process, which is what I want you to take home with you. Okay? Yes, question?
Can you explain the intuition regarding, how did you know to add k plus 1 and n minus k?
How did I know to add k plus 1 and n minus k? So what I'm trying to do is I'm trying to say, look, I have committed to having this B in the null space, okay? I know that I have some dimensional space there, and now I also want to pull out this sigma k plus 1. So I want to be able to make sure that I can find some W of this form. And so I'm looking at my ambient dimensional space. I'm saying, how do I know that I can find an overlap in these vector spaces? How big do I need to make this thing so that I can be sure that it intersects with this? And the only way I can do that is by comparing the dimensions. And that's why I'm adding them. This has nothing to do with rank nullity. Yes?
How we went from the span of one vector, k plus 1, to the whole matrix.
So here, so the vk plus 1 is v1, v2, all the way to little vk plus 1. That's big vk plus 1. And little vk plus 1 is just the kth column. So if I wanted to just pull out the k plus 1th column, everything would be 0 here except for this entry. Why do we have zeros here? Up here? Because W is in the span of this thing, right? So it could have it could have weights on all of these things. It cannot have a weight on vk plus 2 because it's not in that span. It's in the span of this. If it had a weight on vk plus 2, it would not be in the span of this matrix. But it could have weights anywhere here. Okay? So now we have this W. Yes, question?
Can those weights be zeros?
We'll come to that.
Can you explain how W here is in the span of the null space of B?
We've just chosen it to be in the null space of B. Because, and why, we don't know what W is. All we know is that there exists some W, right? We haven't given you a W. We haven't given you a formula. This is an existence proof. We're saying there must exist some unicorn out there that it has these properties. We don't need to know what that unicorn is or its name or its color to use it in our proof. Okay? Does that make sense? So now we're almost done. So what we have here is we know now that W is a unit vector. Okay? Therefore, alpha must also be a unit vector, right? Because V is orthonormal. Now let's go back to what we had up there at the top. And we have norm of AW, the Frobenius norm, or no, sorry, the 2 norm, is equal to U sigma V transpose V alpha, which is equal to U sigma alpha. Everyone with me till here? This is we've already done. Okay. Now, U is an orthonormal transformation. Right? There's an orthonormal, this is some vector. Sigma times alpha is some vector. I don't care what it is. Does an orthonormal transformation ever affect the norm of a vector? No. Can I get rid of this U?
Yeah.
So this is equal to the norm of sigma alpha. Okay? Now, sigma times alpha, what can we say about sigma times alpha? Sigma is all of these singular values along the diagonal, right? So how can I write this out? This is equal to sigma 1, basically I'll just write the sigma 1 squared, alpha 1 squared, plus sigma 2 squared, alpha 2 squared, plus dot, 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 all the way up to sigma k plus 1 squared, alpha k squared, or k plus 1 squared, right? After that, the alphas are 0. Everything else is 0. So this is what we have. Right? Sigma is of this form. Let's say A was tall, and you have basically non-zeros here, and then zeros everywhere here. This is what sigma looks like. Yes?
How did you get rid of the square root?
Oh, yeah, sorry, there should be a square root. Now, I want to prove that this is greater than or equal to what? Sigma k plus 1. Okay, good. So this is the same kind of thing we've seen before, right? We've done this kind of thing now multiple times. Right? What do you do? What's the trick that you do? You know that the alpha i's sum to 1. So what do? I want to say that this is greater than or equal to something. If I wanted to upper bound this, if I wanted to say it was less than or equal to something, which sigma would you choose? Sigma 1. But I want to say it's greater than or equal to something. So that means this must be greater than or equal to sigma k plus 1 squared times the sum of the alphas squared. But this is equal to 1. Therefore, this must be greater than or equal to sigma k plus 1. This is exactly the same argument we've done now twice in class already. We're not necessarily picking the vector vk plus 1, correct. We could not pick vk plus 2 because then this argument wouldn't work. Then you would need a sigma k plus 2 to show up in that. And then your sigma k plus 2 is smaller than sigma k plus 1.
But this part is after you define the matrix vk plus 1.
Right, but if I had a non-zero here, then this inequality would not work. Right? Okay, so recap. What did we do? We first said we're going to take this matrix norm problem and we converted it into a vector norm problem that was easier for us to deal with, okay? Then we said, okay, I want to find a w that makes my life easier, right? This inequality here, this is true for every w. So I'm going to choose my w. I'm going to choose my unicorn that helps me. I don't need to find a formula for that unicorn. I just need to prove that it exists. So I'm going to choose a w that belongs to the null space of B, but I also want to pull out this sigma k plus 1. So I'm going to make sure that I have a w in such a way that that sigma k plus 1 comes out, right? And for that, what I want to do is I want to be able to say, look, you know, there's some vector space here that's the null space of B. There's some vector space here where that includes vk plus 1. And I want to be able to pull out that vk plus 1. But just considering vk plus 1 is not big enough, right? So I kind of augmented it to look at the entire the span of v1, v2, all the way up to vk plus 1, so that I can ensure that these two vector spaces overlap. There exists my unicorn w that allows me to then go through the computation, right? From here on out, this is just algebra. The conceptual part of the proof is all happening here, okay? This is just matrix norm manipulation, right? This is just like using the properties that we've proved. But step by step, we have constructed this in a way that allows us to kind of get to the result that we want. And none of these steps did we say, like, I magically dream of a w. Like, there was none of that. Every time we made a move, it was for a reason. We tried something, it didn't work, and we kind of adapted to move towards our goal, okay? That's what I want you to see here. Everyone with me? Questions? So the question is, why is the dimension of null space of B greater than or equal to n minus k? So the rank of B is less than or equal to k, right? So the rank of B could be 0. If the rank of B was equal to k, then the dimension of the null space of B would be equal to n minus k. No, alphas are not 1. The sum of the alphas is 1 because alpha is a unit norm vector.
Oh yeah, so like,
Sum of the alpha squares is 1.
yeah,
So we've only done half of the theorem so far. There's the entire Frobenius norm proof to be done now, right? So how does this connect to the case of the Frobenius norm? Okay? So there is a proof that is given for the Frobenius norm that is very simple, and that some of you might come across. The problem with this proof is that it's wrong. And before we go into the correct proof of the Frobenius norm, I want to show you this wrong proof, okay? Just so that you can kind of see what's going on. So what we're trying to do is we're trying to say, let's look at the min of A minus B, where B is of rank, or I keep writing this the other way around, rank of B is K. Okay? And then you can write this as min of, you follow like this proof follows kind of the same, in some sense, the same strategy that is a good strategy to use. When in doubt, use the SVD basis, right? Kind of that's what we did in this 2-norm proof as well. We said like, oh, it might be useful to think of W in the SVD basis in the case of it, like how does it relate to V? So let's write the SVD of A. So instead of A, we write U sigma B transpose minus B. Okay? Now this is a Frobenius norm. Is the Frobenius norm invariant to orthonormal transformations? We proved this last time, right? Does it matter if I multiply the entire thing inside the Frobenius norm by an orthonormal matrix? No. Frobenius norm does not change, right? So I can write this as min U transpose U sigma V transpose V minus U B U transpose B V. Right? I left multiplied by U and I right multiplied by V. Or left multiplied by U transpose to be precise. Okay? So this is now equal to the min of sigma minus U transpose B V Frobenius norm. And remember, this is over B's that are of rank K. Okay. So this is kind of nice now, right? What is sigma? Sigma is basically, almost everything around sigma is 0. Right? So computing the Frobenius norm of sigma is a particularly easy thing to do. Right? And then I have this thing here. So maybe I should just write this as min over minus B twiddle Frobenius norm. My rank of B is still equal to K, and I have B twiddle is equal to U transpose BV. I just give it a different name, right, to make it easy to think about. Okay? So now I have this like matrix that is basically 0 everywhere, minus this B twiddle, right? And I want to minimize this thing. Okay? So, and I get to choose B, right? I get to choose B twiddle. Is it in my interest to put non-zero things in B? Only a little bit, right? Only kind of like if this has a 0 somewhere, then I want B to also have a 0 there, right? So it's kind of natural to only want to consider diagonal B's, right? Or almost diagonal B's. So if you wanted to minimize this, what B twiddle would you consider? Like remember, sigma is something like that looks like this. Sigma looks like sigma 1, sigma 2, sigma r, and then zeros here, and zeros here, and zeros here, right? So would I ever choose to put a non-zero element along in a non-diagonal spot on B if I'm trying to minimize this thing? No. Makes no sense, right? So then what is the natural minimizing B twiddle that you might want to choose? Sigma. And if I choose B twiddle equal to sigma, then, well, what's the one constraint that I have? I want to choose a rank K matrix, right? So how many singular values am I going to choose? I'm going to choose the K. Which K ones do I want to cancel? Which ones do I want to cancel? Do I want to cancel the big ones or the small ones? The big ones. So I'm going to choose sigma 1 to sigma K, right? The big singular values. Cancel those out. And so I get exactly what I want, right? What is then B twiddle going to give me out? It's going to give me exactly that AK, right? It's basically just the top k singular values and the corresponding singular vectors. Such a nice proof, right? We spent 2 lectures doing this. So just to write this out, so choose b twiddle equal to sigma 1, sigma 2, sigma k, 0, 0, 0. Therefore, b is equal to sorry, go ahead again. So I'm going to get some u sigma kb transpose, yes. Okay, so something is going on here. Some of you are like, something is suspicious. I gave you a hint as to what is. I mean, I preface this with this is a wrong proof, right? So either like I'm pulling a really early April Fool's joke, or something is going on. And what's going on is, yeah, you want to say something?
Does that seem the rank of b is k or less than k?
I'm using equal to k because it makes my life a little bit easier, but the whole thing is true even if it's less than or equal to k. Yeah. Does sigma have n singular values? I'm thinking here of sigma having only r singular values, but I'm thinking of k less than r. So rank r. But it wouldn't matter even if you chose n. It's not a thing. Okay. So, yeah, last comment.
Is there any difference here between like taking the argument or just
Is there any difference here between taking the argument and the min? There I was writing argument, here I'm writing min. No, I was just a little lazy. I didn't like saving the arg everywhere, but I'm just trying to get across the point of that what b would you choose to minimize this, but I could probably just write it out with arg min and b. Okay, so here we had this thing where you had u transpose bv, and we said, oh, let's just call that b twiddle, right? It's a harmless renaming. And then we said, oh, let's restrict our search to b twiddles that are of the diagonal form, because it makes no sense to put zeros anywhere else. But now, remember that we have a rank constraint on b, right? We have a rank constraint on b. And so what we're saying is that we want to have a rank constraint on b, and we want to be able to re-express it in terms of u transpose bv, and have that end up be a diagonal matrix. That is something that is not necessarily feasible. So basically, what I want to say is that we cannot say what we said without loss of generality. I said basically, assume b twiddle has no has only diagonal entries, right? I kind of said that, and I kind of gave some hand-waving argument for why this is true, right? But why am I allowed to say assume that b twiddle has only non-diagonal entries? Because if I was taking a general matrix, then yes. But now I have this rank k constraint, right? So for example, if I was to choose consider the matrix b1 twiddle with 1, 1, 1, 1. Okay? And what I want to do is I want to basically say, oh, let's remove the non-diagonal entries because they're only harming my norm, right? Let's say I was starting out with this value for b twiddle. 1, 1, 1, 1. Some hypothetical thing. But clearly I can only do better by removing the non-diagonal entries, right? So I would say that a better argument would be B2 twiddle, where I have 1, 1, 0, 0. Right, by the argument I just gave you, do you see why B2 twiddle would be a better B2? By removing the non-diagonal entries, what have I done to the rank of this thing? I have increased the rank. Now, am I keeping my rank constraint by just generically removing these non-diagonal entries? Right? Do you see how, because we have the rank constraint in the minimization, we cannot, without loss of generality, say that, oh, let's just assume that there are zeros everywhere but the diagonal, that B twiddle is just a diagonal matrix. Because we're not considering in that argument, when I say that without loss of generality, I'm not considering the interaction with the rank constraint. So this is a very, very subtle thing that often, if you read something on the internet or something like that, it'll just push it under the rug. It'll give you this proof and say oh, obviously, therefore, the top singular values are what matter. Does everyone first are you following what I'm saying? Yes? Question?
So sigma is rank n or rank k?
Sigma is rank R. Sigma is the same rank as A.
Okay, so setting b tilde equal to sigma won't necessarily work with R.
Well, I'm setting B tilde equal to the top k singular values of that, right?
Right.
Right.
So, but isn't that necessarily rank k?
That is necessarily rank k, but I'm saying that without loss of generality, assume that B twiddle is diagonal. That step itself is wrong. Reducing our search space to say that we can get the same thing by only looking at non-diagonal matrices is wrong. That's where the mistake is. It's not after that assumption. It's in making that assumption. That assumption is invalid because of the rank constraint, because of this counterexample here. Because removing and changing the diagonal entries can lead to a change in the rank.
But we know the rank of that, right? It is k.
We know the rank of it, but you cannot assume that it's diagonal.
But isn't it defined as diagonal and it has rank k?
No, that you cannot define it that way. You cannot. That's the point. You cannot. That's not allowed.
But we know the singular values exist, right? So doesn't it exist by construction?
Okay, hang tight. I'll take some other questions. Yeah. Yes?
Why can't we just choose diagonal matrices?
Why can't we just choose diagonal matrices where?
For B twiddle.
If I was to say that B twiddle is, if I restrict my search space to being only diagonal matrices, I might necessarily be looking at matrices with larger rank. Right? So I need to simultaneously satisfy my rank constraint and restrict to diagonal. And I cannot simultaneously do that. I cannot say that there is no interaction between my rank constraint and restricting to diagonal matrices. Right? Here when I say assume B twiddle has no diagonal entries, I cannot say that without loss of generality because of this rank constraint. If I had no rank constraint, I could say that without loss of generality. But because this matrix might be a valid matrix. If let's say my k is 1, right? This matrix is valid as a choice for B twiddle. This matrix is not. And so if I restricted my search space to matrices that looked like this, I'm not allowed to do that, basically, because I'm now violating my rank constraint. And basically, in that step, from there to there, I'm ignoring my rank constraint. I'm pretending it didn't exist when I'm making that assumption. Does that make sense? Other questions from people who, especially people who haven't asked questions? Yes?
You mean the rank of U transpose B weight can be less than K?
The rank of U transpose BV can be less than, it can be greater than K. That's the bigger. Less than K is totally fine, but by removing these diagonal entries, I can increase the rank, which I'm not allowed to do. Reduction in rank is totally fine.
I think you multiply by a formula matrix. It may not change the rank.
It will not change the rank, yes, I agree. But the restriction to diagonal is what we're talking about.
But why you can't that you can look for BV equals a diagonal?
You cannot, because by doing that, you might not be satisfying your rank constraint. Okay? Yes?
So when you pick a higher rank, does that mean you're decreasing your search space, or are you expanding it outside?
When I pick a higher rank, I'm simply violating my constraint. So I'm going into something infeasible.
So if you have like a search space of like 1 dimension, and now you're going into 2 dimensions.
I'm not going into 2 dimensions necessarily, because I'm saying that I'm only allowed to look at matrices that are of a particular rank. And I'm now creating matrices that are of a different rank. And that's not allowed. So I'm not sure that there's a dimension. And it's not about expanding or compressing the search space. I'm not sure that there's a good way to think about it from that perspective. Yes?
Kind of relating to that, if you like change the rank, how would that affect the minimization? Is there like a correlation, like increasing rank would necessarily like decrease?
So, okay, great question. So, is there a correlation? Is increasing rank necessarily going to decrease my minimization? The answer is absolutely yes, right? For example, here, this I think will help. If this K was equal to N, okay, what is the value of this minimization? Forget the argument. 0, right? So if I could choose AK to be exactly A, if A is rank N, find the best rank N approximation to a rank N matrix, it's the thing itself. There's no approximation error at all, right? So increasing rank will always make me do better, right? That's why that rank constraint is so important. Make sense? So this is one of those things that you have to sit down and think about and really understand why this is subtly wrong. And this is why this is such a powerful argument, because you can really think that this is working, but the error is subtle. And the reason I want to point this out to all of you is that there's a lot of times in your life where this will happen to you. It might be a proof, it might be something else, but something will not make complete sense to you. And it's okay for you to question it, right? It's okay for you to say hey, I need to understand this. I want to understand what's going on. Ask questions, be critical. If you don't understand it, it might be because it's wrong. It might not be you, okay? Just because someone says something on the internet or says something in fancy language or puts a charming bow on it does not make it correct, right? Believe in yourself to question these things, and there's a lot of value in developing that internal perspective. That's the real reason I really want to get through this. Question, yes. Is it possible to find a B tilde such that that maintains the rank constraint and does this? So it might be possible, but that requires a proof, right? Which is not here. And to prove that, basically you have to go through the other proof that I'm now going to give you, right? So, yeah. Okay. Now, we're going to do a correct proof. Okay, so I want to get through this other proof. This one is actually correct. So, let's understand this, okay? So now we want to consider the Frobenius norm, part 2, and we want to say that the argument of this is given by AK as well. So let's do the same thing we did last time, which is first consider what is the Frobenius norm of A minus AK, right? And I know that A is basically sigma, or the sum I going from 1 to R, I guess, of sigma I, ui, vi transpose. And this is just the top K singular values. So this is sigma I, ui, VI transpose. Okay, so when I take this difference, this is just the sum I going from k plus 1 to r, sigma I ui VI transpose. Okay? So now when I look at this, this is just basically, I can write this as a diagonal matrix, right? It's basically a U times a diagonal matrix times a V transpose. And so, like, this is basically U times a thing with, this is 0, 0, 0, and then sigma k plus 1, all the way up to sigma r, 0, 0, 0, and then V transpose. That is what this is, right? Because I basically removed all of the top k top k singular values. So what's left is only k plus 1 to r, right? And so when I think about this, the Frobenius norm of this thing, this U transformation doesn't matter. This V transpose transformation doesn't matter. So all that I get is this is exactly equal to the sum of the singular values squared. I is going from k plus 1 all the way up to r. Okay? Everyone see this? Remember, the Frobenius norm is invariant to orthonormal transformations, so we're using that here. And it's just the sum of the squares of the elements. So that's all I did. Okay. So I have this now. I guess as an aside, I can just say this, right? Like in general, if I have the Frobenius norm of a matrix A, this is just equal to the Frobenius norm of sigma, because I can write this as U sigma V transpose, but the U and the V transpose don't matter because it's an orthonormal transformation. And this is just the Frobenius norm of sigma, which is just the sum of the singular values. So that's exactly the same logic that I'm applying here. So I can now see that what I want to show is that this is the lowest this quantity can be, right? And so in the same vein as how we did the other proof, we want to say now for any B such that rank of B is k, I want to show Frobenius norm equal to k plus 1 to r. Okay? Yes? Square, yes. I should say squared, 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 squared. Yeah, I should say squared, 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 so that I don't know how to draw square roots. Good point, thank you. Because the Frobenius norm is the square root of this, right? So I forgot to write the squared. Sorry, thank you for pointing that out. Yes, question?
How did you separate out the norms?
Which norms?
A minus AK is equal to, like, the
Those are just summations, so just the definitions of A and AK. I'm just writing the outer product form of the SVD. Yeah, for now, if it's not clear that this, what happened here, just accept it. I will answer that question later. There's no separating of the norms. I'm literally just computing the Frobenius norm of this, using the fact that the Frobenius norm is invariant to orthonormal transformations. So now I know the fact Okay? Let's look at this, what we just said here. The Frobenius norm of any matrix, this might help your question too. The Frobenius norm of any matrix, what we just proved, is equal to the sum of the squares of its singular values, right? Because we proved last time that the Frobenius norm is invariant to orthonormal transformations. Okay? So when I think about the Frobenius norm of this matrix here, okay? Yeah, I should have squares everywhere, sorry. Thank you very much. When I think about the Frobenius norm squared of this matrix here, I can think about it in terms of the singular values of that matrix itself. So for example, if I set A minus B equal to some matrix C, right? I can think about the Frobenius norm of matrix C as equal to the sum of the singular values of C squared, right? Just sigma I of C is equal to ith singular value of C. So what I have here is a bunch of singular values. Yes? Okay, good. And this is going from I equal to 1, let's say, to n. Okay? I can write this as going to n because even if I have only r singular values that are non-zero, the remainder are going to be 0. So it doesn't matter if I write this sum going to r or going to n. It'll just make my life a little bit easier to write it going to n. But it makes no difference to my summation. Yes, question?
Should that
Yes. Thank you. Sorry, I don't know why I'm forgetting squaring today, but clearly it's not coming. Okay, everyone with me here? Everyone understand this step? Thumbs up, thumbs down? Okay, good. So I'm going to compare this thing to this thing. And what is this thing? These are the sums of the singular values of the matrix A, right? Okay? Squared. Squared. Sorry. I'm sorry. I'm really sorry. I don't know why I'm doing this. But I'm now trying to compare these two things. Okay? And so here I have a sum of n things. And here I have a sum from k plus 1 to n. Okay? So if I wanted to do some kind of comparison, one thing that would be convenient for me is if I could compare these element by element, for example. And if I could say that, every element of this is, for example, greater than every element of this, then I would be done, right? So if I could show somehow that if I could show that sigma I of the matrix C is greater than or equal to sigma k plus I of the matrix A. Okay, so I compare the first term of this to the first term of that. What is the first term of this? Sigma 1 of C, right? What is the first term of that? Sigma k plus 1 of C, right? Okay, everyone pay attention because this is you'll get confused and then you'll have questions. So first term of this compared to first term of that. So sigma 1 to sigma k plus 1. Sigma 2 to sigma k plus 2. Which of the two sums has more terms? This one has more terms, right? So where am I going to run out of terms there? I'm going to run out of terms with this term first. And I want to prove this is greater. right? So if element by element I prove this, then I'm done, right? If I can prove this, that implies this, then my proof is done. So now I've reduced this to showing, to making a proof about the singular values of two specific matrices. Okay? Does that make sense to everyone? That as long as we prove this, we're done. This is sufficient? Okay, good. Okay. So let's think about this sigma k plus I of A. Okay? So I can think of this as basically the k plus ith largest singular value of A. Right? Nothing special there, we know that. But I really want to think about this as A minus a k plus I minus 1 2 norm. So if I was to try and do this best 2 norm approximation, right? I want to say I want to find the best k plus I minus 1th approximation. How could I do that? And what will that be? That's going to give me exactly this, right? I want to find, like the k plus ith largest value, singular value, means I've removed all the singular values before, right? Removing those is basically the same as removing this matrix, right? Which is our best approximation that we proved in the spectral norm case. Okay? So this is one ingredient that we're going to use in this proof. And I want to think of this singular value over here in terms of this. How much time do I have? Oh my gosh, again? Okay. So let's see if I can get this done in a couple of minutes. So now if I consider sigma I of C, okay? This I'm going to think about now as, can I think about this as C minus Ci minus 1. So for any C matrix, I can do the same thing, right? The ith singular value is what remains after I remove the best I minus 1th rank approximation, right? Exactly what we did in the previous case of the spectral norm. Okay? This I write as A plus B minus Ci minus 1 minus B. I did nothing. I added a B and I subtracted a B. Did I do that? No, I didn't do that right. I'll just write it as this. C is equal to A plus B. So I did nothing here, really. Sorry, A minus B. Okay? It's equal to A minus, let me call this some matrix D. Let me call B plus C minus I minus 1 to be equal to this matrix D. So I'm saying C is equal to A minus B, right? And now I'm saying call B plus C is some matrix D. That's all I'm doing.
Wait, what's the indication like D like that line two? Is that the norm?
This is the norm of A minus D.
I'm sorry.
Yes?
Why did we switch to 2 norm?
Why did we switch to 2 norm? Because we're saying that the ith singular value is the best, is what remains when you remove the best I minus 1th approximation. So we're using our result that we just proved here. So we're saying that now we've moved from showing something about the Frobenius norm to showing a relationship between singular values. Right? And so we're using the characterization of singular values as given by the spectral norm. Right? Because the spectral norm is basically the largest singular value of a matrix. Right? So if I think of this matrix C minus Ci minus 1, the spectral norm of that is given by its largest singular value, which is sigma I. Okay? So that's what this I'm trying to say. This is for some generic matrix A, but I'm applying it here for the matrix C. Now, the homework problem on your first homework or your second homework. What is the rank of Ci minus 1? At most I minus 1 by definition, right? What is the rank of B? By our at most K, right? So therefore, what is the rank of D? Must be at most K plus I minus 1, right? Okay? So now I'm looking at A minus some matrix, which is at most rank K plus I minus 1. What is the best rank K plus I minus 1th approximation? Have we done this kind of thing before? So, and we're looking at the 2 norm of this. So what are we going to get out? K plus I minus 1 plus 1 gives me K plus I, right? So the best, what is the best you can do if you have only K plus I minus 1 things to approximate? What's going to be left over? The K plus ith singular value is what is going to be left over, right, in the norm sense. Which is exactly what we have here. This is exactly what we have here. So here, the K plus ith singular value of A is A minus the best K plus I minus 1th approximation, rank approximation. Okay? So this must be greater than or equal to sigma K plus I of A. So what we're doing is we're using this result to prove the result for the Frobenius norm. Okay? So I'm 1 minute over time. I'll end here. Come to office hours if you have questions. Thanks.